Hello, everyone. Welcome to the Bayesian longitudinal data modeling workshop. Let me first share my screen. Okay. My name is Cynthia Tong. I'm an associate professor in the Department of Psychology at the University of Virginia. After this workshop, if you have any question, feel free to reach out to me by this email or just come to my website. As you probably have already found from the schedule of this workshop, there are 3 parts. The first part is about Bayesian growth curve modeling, and in part 2, I'm going to cover Bayesian growth mixture modeling, and in part 3, we're going to really practice what we've learned by using R and RJAX package. So we start from Bayesian growth curve modeling, and in this part, we will be able to learn what are longitudinal data, what is growth curve modeling, how do we conduct growth curve modeling in Bayesian, and how do we handle missing data in Bayesian, and how do we handle non-normal outcomes in Bayesian analysis of longitudinal study. At first, let me just give a very brief review about what longitudinal data are. So longitudinal data basically help us to understand changes. Unlike one-off cross-sectional studies, which give us information about subjects at one time point, like a snapshot photo, longitudinal studies follow subjects across time, more like a photo album. They tell a story about subjects not only at a moment in time, but also over time, showing how subjects have changed and what factors can cause between subject variations in change. And to compare longitudinal data with other types of data, we can take a look at this Cattell's data box. It has 3 dimensions, and those 3 dimensions are persons, variables, and time. Okay. Based on our research question, we can fetch a slice from the data box. For example, if our research question is what correlated with success in graduate school, we may want to collect data on GPA or GRE scores, and maybe mom's education level from a number of students, and then do a multiple regression to figure out which variables have higher influence on the success in graduate school. And in this case, we basically collect data from multiple subjects, multiple people on multiple variables, but only at one time point, or sometimes maybe 2 time points, a limited number of time points. It's a slice from this data box as shown from here. So we have multiple subjects and multiple variables. And this is called a cross-sectional data. And similarly, based on other research questions, we may want to analyze data from one person or very few persons, but with multiple variables at multiple time points. And this slice from the data box is called time series data. And we have one slice left upper here, right? So we can see these data are collected from multiple people at multiple time points, but only at very limited variables, few variables. And the name of these data are longitudinal data. And longitudinal data are actually very useful in distinguishing patterns of change. If we just look at the coordinate plot with cross-sectional data, our conclusion for this, in this coordinate plot, our conclusion would be Y decreases as time increases. But if I'm telling you that these 6 dots did not come from 6 different individuals, instead, they come from 2 individuals, and each individual were repeatedly measured for 3 times, like this. Well, you may still get a conclusion that Y decreases as X or time increases. But the same data points may show different patterns. For example, if the data were coming from two subjects who are like this. And then we see that for one subject, Y increases as time increases, and for the other subject, the Y decreases as time increases, right? And it is possible that for some of the cases, their scores are just fluctuating up and downs like this. But basically, longitudinal data are just possible to give us information about the patterns of change. In general, longitudinal studies have two main objectives. The first is to investigate intra-individual change over time. That is about how individuals change throughout the duration of the study. And the second objective is to investigate inter-individual differences in intra-individual change. We can examine factors that influence heterogeneity among individuals in how they change over time. And longitudinal data have gained more and more popularity and are widely used in many disciplines, including psychology, education, environmental science, political science, medical research, etc. Growth curve modeling is commonly used in longitudinal studies because it can directly investigate intra-individual change over time and inter-individual differences in intra-individual change. Growth curve models, or GCMs, are a collection of models for investigating the change of trajectory of phenomenon. It can be viewed as a special case of multi-level models and mixed effects models. And they also can be used as building blocks for more complex models. And growth curve models usually go by a number of different names, such as mixed effects models, multi-level models, random coefficients models, hierarchical linear models, latent growth models, but these models are all algebraically identical with various statistical computations. If you want to know about the development of growth curve models, here are some of the references you can check. So basically, it can date back at least to 1958. And if you're interested in the history, you can read Singer and Villett's book, Applied Longitudinal Data Analysis, or just read a chapter written by McCardle and Nesserode about these overviews. These overviews just provide a good way to help us understand the history of growth curve modeling. And the research of growth curve modeling is still growing. Some recent development of growth curve models include dealing with non-normal data, missing data, and so on. And I've listed some of those. That's about Bayesian growth curve modeling. To construct a growth curve model, we can think about it in this way. So if a group of participants all have a linear change pattern, we start from a linear growth curve model. So if they all have a linear change pattern, then we can fit a linear regression to each person, right? So here, this YIT represent the observed score for the I subject at the T time point. So basically, we regress the observed scores for the subject on time T. Okay. This is a linear regression. So we have intercept B0I and the slope B1I because we have the subscript I because this could be different for different individuals. And it can be represented by this plot. So basically we have the observations for the individuals for this one individual at 4 time points, and we fit a linear regression line to these 4 observations. And this is a individual growth curve. And the Merriman errors, which are represented by EIT, are those vertical red bars. And this is just for one individual. And if all individuals are mirrored at a common set of time points, and then we would have this matrix format. So basically, all these individual scores are regressed on time, but then they have individually different intercept and slopes. Okay, so basically each individual may have a regression line, and we can average them to get the average linear growth. This above equations basically resembles a factor model with two factors and a known factor loading matrix. Those two factors are latent intercept and latent slope, and the mean of the latent intercept and latent slopes are the average intercept and the average slope respectively. And the variance of the latent intercept and slopes can also be estimated. They indicate the between subject variations in intercepts and in slopes respectively. For the simplest case, we have this random intercept and random slopes equals this average intercept and average slopes plus the random component. Okay. And this is also called an unconditional linear growth curve model. In general, the first level of growth curve model is not necessarily to be linear, so it can be specified as a YIT, as a function of time and latent coefficients, plus the within person measurement errors. Okay. And this YIT again is a measurement for the individual I at time t, and this function f is a function of time representing the growth with individual random coefficients. Okay. And then for the second level of growth curve models, we basically model this random coefficients BI using like B times XI plus random component. Here, this XI is a design matrix with the first columns are all ones, and all the other columns are the data for the covariates. So if you don't have covariates, then this XI will just be a column of one, a vector of one. And B is just a coefficient matrix that we're typically interested in to estimate. All right. And different growth curve models can be constructed by specifying different growth functions. For example, a linear growth curve model, the growth function f of t and bi is just the intercept plus slope times the time t. Okay. Notice that these intercept and slopes are all random because they can be different for different subjects. And for quadratic growth curves, it is B0I, which is a intercept, and B1I times t, that is the coefficients for the linear term, and B plus B2I times t squared. So that's the quadratic growth curves. And for latent basis growth curves, we specify it like this. So the function is B0I plus B1I times AT, where AT needs to be estimated. So basically the basis of the growth curves can be estimated. In that way, it's not necessarily for the change to be linear, it can be nonlinear. Okay, and there are also some other nonlinear growth curve models can be specified. The only things like you just need to specify this function in a different format. Okay, so how do we conduct a growth curve modeling in Bayesian? Later in the lab session, we're going to have an example data from the NLSY, National Longitudinal Survey of Youth 1997 data. It's about P-body intelligence, so PIAT math scores, achievement test scores. And the data comes from 434 subjects, and they were measured from 7th grade to the 10th grade. So there are 4 time points. There are also actually missing data in the data set. We're going to talk more about missing data in a minute. But basically, this is the data set we can play with in the practice session later. And as you can see from this trajectory plot, basically each trajectory represents one person. And in general, it seems like there is a increase in the math scores from 7th grade to the 10th grade. And in the lab part for illustration, we're going to fit 3 models to the data. We're going to work on the linear growth curve model, quadratic growth curve model, and latent basis growth curve model. Because of the time limit of this workshop, I actually assume that you're already familiar with R and you can easily read RJAX code. As a preparation, I already uploaded how to install R and RJAX Moodle website, so you can follow instructions to install all the required software. And then here, I'll just briefly introduce the JAX code, and then later in the practice session, I can explain a little bit more about that. Okay, so for JAX code, to specify or to conduct Bayesian analysis, we need a few important components. The first part is your model part, and you basically specify your model in JAX. And the second, you have to have your initial values and your data set. So basically these 3 parts, and then you compile them and running and JAX will help you to analyze your model and estimate all the parameters. Okay, so here I will just talk about the model part, like how you specify your model. In JAX, this model part for the linear growth curve model would just be like this. In this model part, we first specify our model or the likelihood, and then we put our prior informations in, and finally we can reorganize the parameters and to let just for us to easier track which parameters we want to estimate. Okay, so for a linear growth curve model, this part is really just like how we specify our model or the likelihood. And you can see like this is for individual, like for the I subject, basically for I from 1 to n, and this is the total sample size. And for each of the subject at each time point, for t is from 1 to 4, there are 4 time points for this data set. And our observed score YIT follow a normal distribution with a mean of mu of y, and this is the precision parameter, basically it's the inverse of the variance. In JAX, it's just, we're not actually specifying the variance, instead it's the precision parameter. Okay, this is, and then the mu of y, or this mean of y, can be represented by a linear relationship with time t. So it's the latent intercept, LS1 plus latent slope times t. Okay, and then for the latent intercept and latent slope, together they follow a multivariate normal distribution. That's the mean of intercept and slope of the intercept, and also the covariance matrix of intercept and slope. Okay, so in this model, we have parameter mu ls. Well, we can actually call it like BL, BS. Okay, and also the covariance matrix of the latent intercept and slope, and also this precision parameter. Okay, this is actually also the inverse of the covariance matrix. Because we have these many parameters, then in Bayesian, we had to specify priors for them. And here we just use a non-informative priors where all the fixed effects, the intercept and slope, we just use a normal distribution with mean of 0, and precision, a very small precision, basically the variance is 10 to the power of 6. The precision is 10 to the power of -6. And then for the precision matrix, which is the inverse of the covariance matrix, the prior is follow a Wishart distribution, and the Wishart distribution are just specified in this way. And the precision parameter, which is the inverse of intra-individual measurement error variance, follow a gamma prior with parameters like 0.01, 0.01. So they are really just like more like a flat distribution. So it's non-informative. But what we really care about are the parameters of the variances instead of precision. So after we specify the priors stopped here, we transform all the parameters. So instead of having the inverse of the variance, inverse or the precision parameter, we take the inverse of it and transform back to the variance parameter. And we take the inverse of the precision matrix, we get the covariance matrix. And then we save all these elements in this covariance matrix into the variance of intercept, variance of slope, covariance between intercept and slope. And we can also calculate the correlation between intercept and slope. Okay, so that's how we specify our model for a linear growth curve. And for quadratic growth curve model, it's just similar. Here, for the subject I from 1 to n and the time points from 1 to 4, the YT still follow this kind of distribution, but then because it's a quadratic growth curve, so the mean of Y is actually quadratic form of time. So we have the LSQ1, which is like the intercept term, and this is a coefficient for the linear term times t, and then this is a quadratic coefficient times t squared, or t times t, okay? And then these random coefficients together follow a multivariate normal distribution with 3 dimensions, and then we have these 3 means. So we have to specify priors for all these 3 parameters, and then we specify prior for the precision matrix, and then in the same way we just transform it back to the variance, covariances, and that's how we do it. And for the latent basis growth curve models, we'll see that instead of having the mean of Y model using a linear form of with respect to time, we have this mu of Y equals LS1 plus LS2 times A of t. So this A of t can be estimated. We just need to fix the first latent basis and last latent basis, and we freely estimate all the other latent bases. So the first latent basis is fixed at 0, and last is fixed at 1, and all the others are parameters, so we specify priors for them, and everything else is the same. Okay, so we'll have a Q&A session at the end, or actually in the practice part. If you have any question, I'll be happy to answer those. Okay, so after we fit models to the data, in Bayesian, we can do a model comparison using DIC, like deviance information criteria. It's just like AIC or BIC is the Bayesian version. So the smaller the value of DIC is, the better the model fit is. And JAX actually provide a function to calculate DIC. And for the data set I just showed you, I fit a linear quadratic latent basis growth curve models, and I calculated DIC. And from what we have here, it seems like the latent basis model fits the data the best because it has the smallest DIC. However, what I want to really note here is DIC obtained in JAX is calculated based on conditional likelihood function. And according to previous literature, the marginal likelihood should be used because if we use conditional likelihood function for models with latent variables, the model comparison results are not very precise. Okay, so we will introduce WAIC and LOO cross-validation in the loop package later, which are calculated based on the marginal likelihood function. All right. Like I just said in the previous slide, growth curve models can also be used as a building block of more complex models. So there are many variants of growth curve models. Here's just one example of a recent study of mine. So here in this path diagram, we can see that there are BMIs measured for different subjects and PBF, which is the body fat percentage measured for different subjects. You probably see that there are dashed lines just because for different subjects, they were not measured at a common set of time points, but basically each subjects were measured at quite different time points. Okay. And in that study, we want to know how does the BMI change over time influence the body fat percentage change over time. And also in that study, we also control for blood pressures. Well, actually, there are many other covariates we control for blood pressures and also the sex effect. So in this path diagram, we see that the blood pressures is really just an example of a time varying covariates, and sex is a time invariant covariates. So also we look at the growth of one set of variable how that influences the growth of the other set of variable. And in this study, I particularly use Bayesian method because there are many complications here. Because, for example, all those subjects were measured at a different sets of time points, so they are individually varying time metrics. And also the body fat percentage, it is a percentage data, so it's a proportion data, and Bayesian is just easier to handle that. And all the time invariant covariates and time variant covariates can just be easily added, and with missing data for this data set, Bayesian is just very flexible. So basically for such a complex model, Bayesian shows its advantages. And here I actually listed advantages in using Bayesian method to analyze longitudinal data. First, Bayesian methods are powerful to handle complex longitudinal models and high dimensional problems. Like I just said in the previous slide, this past diagram or this data set is complicated to estimate or to analyze, and Bayesian is just very flexible to do that and very powerful. And also Bayesian methods are relatively less mathematically demanding and easy to implement. And another advantage that is well known is that Bayesian methods can incorporate prior knowledge. And based on some of the previous literature, we see that informative priors really show a great advantage. So if we have prior knowledge and incorporate that really will benefit your analysis. And even it has shown in the literature that for growth mixture models that we'll cover later, like frequentist estimation usually yield poor estimation parameter recovery with small sample size, while Bayesian approach using informative priors, they showed their promise. Okay. And also, Bayesian methods are very flexible to specify missing data mechanisms. We're going to talk about that in a minute. And a Bayesian method can also be able to use to handle non-normal longitudinal data conveniently. And it can be flexibly specified in free software such as Stan or JAX that we're going to use today. Okay. Okay, now we're going to talk about missing data in longitudinal research. In longitudinal studies, missing data are the rule, not the exception. Although at the data collection stage, researchers tried really hard to reduce attritions using various strategies such as planned missingness designs, sending reminders or incentives, but missing data are still not avoidable. A recent meta-analysis examining personality traits reported that 91 out of 92 longitudinal studies had incomplete data, and an average attrition rate across sample is 44%. And retention is particularly difficult for at-risk populations. And in some cases, the missingness proportions can be as high as 85%. When longitudinal data are missing, the data set is unbalanced over time. And it means loss of information, and which is a reduction in efficiency and a drop in precision. And under certain circumstances, missing data can introduce bias and lead to misleading inferences about changes. And different missing data analytical techniques have been developed according to missing data mechanisms. Rubin in 1976, and also Little and Rubin 2002, they defined 3 missing data mechanisms. They are missing complete at random, missing at random, and missing not at random. Here I use YI to represent the score for the observed score for the I subject, and RI is a missing data indicator. So if RI2 is 1, that it just means YI2 is unobserved or is missing. But if RI2 is 0, it means like YI2 is observed. And also here, this YI0 means observed responses, YIM means conventory set of responses or missing responses. So MCAR, missing complete at random, means data missing for reasons unrelated to either the observed data and missing data or latent variables. So the probability of missing is not related to any of the observed, unobserved, or covariates. Example of missing complete at random include the planned missingness designs. So basically, individuals rotate in and out of the study after providing a predetermined number of repeated errors. The number of timing is determined by the design, so it's missing complete at random. Planned missingness design is just to use to reduce the response burden, and then the missingness, because it's not related to the vector of responses at all, then it can be viewed as a random sample of the complete data. In that case, missing complete random data will be relatively easy to handle. For MAR, that actually requires that missingness is related to the observed data, but not the missing data or latent variables. Okay, so this missing data indicator, probability of missing data indicator equals 1, is only related to the observed data and observed covariates. So, an example of missing at random include when participants tend to drop out of a study because their outcome scores, for example, depression scores at the previous measurement are extremely high or low. Thus, the probability of missingness at the T's occasion depends on the observed values of responsive at the T-1 occasion. So previous time point scores affect the later time point scores. So basically the missingness depends on the observed data. And NAR assumes that missingness is related to missing data or latent variables. Basically, if a participant depression scores are missing because they're just too depressed to participate in the study, then the probability of missingness is related to the unobserved, unmirrored value itself. In that case, is missing, not at random. Okay. For longitudinal data, what happens most often is dropout or attrition. Basically, means that if YIK is missing, then this YIK plus 1, K plus 2 till YIT are all missing. So it follows this monotonic missing data pattern. Basically, Y1 is observed, and in Y2, some participants dropped, and Y3 more dropped. But once they drop, they never come back. It doesn't. So in longitudinal study, there are also intermittent missing, but dropout are probably more often. And dropout can be missing completely at random, or missing at random, or missing not at random. It's not associated with any of the missing data mechanism. It's just observed very often in longitudinal studies. So to some extent, MCAR and MAR data are ignorable because problems caused by them can be overcome through sophisticated statistical techniques such as full information maximum likelihood method or multiple imputation method. But missing not at random are non-ignorable because without extra information modeling or modeling specifications, their influences cannot be well addressed. And to deal with non-ignorable missing data, selection models and multiple imputation method with auxiliary variables can be used. But both selection method or multiplication typically requires auxiliary variables or other informations to account for the non-ignorable missingness. In Bayesian, missing data can be really naturally handled. Okay, we can see that this is a form of the, like, we can actually represent the relationship like this. So the probability of your parameters and the model parameters related to the missingness conditional on your data, and the missing data indicator is proportional to a multiplication of these parts. And this is really just based on the Bayes theorem, okay? Again, that's theta actually represented all the model parameters, and gamma represented model parameters related to the missingness. Data is just our data, observed and unobserved data. R is the missing data indicator. Okay, so it's proportional. This sign means proportional. It's proportional to the probability of data conditional on the model parameters. So that's basically the likelihood. And then times the probability of missing data indicator conditional on data and the model parameter related to the missingness, like what can be used to explain the missingness. And then the probability of all the model parameters, that's the prior information. In Bayesian, when missing data are ignorable, then multiple imputation techniques is just automatically implemented because in Bayesian, we just keep sampling from the distribution of the model parameters. So we know the distribution of it, of the model parameter, we just sample them. And then if there are missing data, we know the distribution of the data. So the missing data can be treated as parameters, and we just sample from the conditional distributions. So if you have missing complete at random data or missing at random data, in Bayesian, it's just automatically take care of. But when missing data are non-ignorable, selection models can be used to account for the unobserved factors that it may explain the missingness. For example, we can actually have a add-on selection model with the probability of Y is missing, or the probability that the missing data indicator equals 1 can be modeled as a linear combination of the current value of, well, the missing value itself and also the previous value. So this is just an example of it. If you have additional covariates and you think the covariates can be used to explain the missingness, then you can add that covariance here to explain the missingness. That's just an add-on models to the original model structure. So basically in Bayesian, that's why I say Bayesian method is really flexible and relatively easy to handle missing data and to specify any kind of missing data mechanisms. Okay. And besides the missing data, Bayesian analysis are also very flexible and powerful to handle non-normal outcomes. There are different types of non-normal outcomes. Today, I'll just briefly talk about some robust growth curve modeling in Bayesian. And in this robust growth curve modeling, basically the data can follow non-normal distributions where they may have outliers or contaminated by outliers or leverage observations. There are different strategies that can be used to handle those data. But in addition to that, sometimes the outcome variables are systematically non-normal. For example, they are just binary, or they are proportion data, or they are const data. So in that case, we can't just simply use the traditional growth curve model to deal with that. Instead, we have to really take the binary feature into consideration. We have to take the proportion feature into consideration. We have to take the cont feature characteristic into consideration. And Bayesian is just very flexible to handle those. First, let's look at robust growth curve modeling in Bayesian. Although normality assumption makes longitudinal models relatively easier to estimate, in empirical data, they are just rarely normal. Sometimes because of a non-normal population distribution, the distribution itself is just skewed, like the reaction time or so. Or sometimes they are just data contamination. There are potential outliers in the data, so your data will never be normal. When data are not normal, but you analyze your data as normal data, there are problems. For example, here's a simulated data from a growth curve model. On the left panel here, we actually simulated 200 subject scores at 4 time points from T1 to T4. And these are just the growth trajectories of the simulated data. And also, these are the box plots of the data. So we see that there are potential outliers only at T1, but not at the others. And by fitting a growth curve model to the data, we see that the slope is 0.208 and it's significant. So there is a significant increase from time 1 to time 4. Okay. And on the right, it's actually the same data set, but I randomly selected 10 subjects from the 200 subjects. So I randomly selected 10 of them and replaced them by multivariate outliers. So for those outliers, they were generated from another growth curve model. It's similar to the first original data, but the only thing is the slope is negative instead of positive. Okay. So those 10 observations or 10 trajectories were marked in red. As you can see from the trajectory plot, if I didn't mark them in red, you can hardly tell there are outliers just because those outliers are multivariate outliers. They can be well hidden in the two-dimensional plot. Okay. And also from the box plot, it's quite comparable to the first, to the original data. Probably wouldn't tell if there's any difference. So here's the outlier. Seems like this is also an outlier, but other than that, they're pretty close or pretty similar. But if you fit a traditional growth curve model to the data, then you will see that the estimated of the average slope is 0.096 and it's non-significant. So with 10 outliers in this data set, and if we analyze the non-normal data using the traditional method as if they were normal, then we get a different conclusion. Okay. So that's why the robust analysis is needed in practice. There are several robust growth curve modeling strategies in Bayesian. For example, we can use robust growth curve modeling using student t-distributions, where in this model, instead of assuming that all the intra-individual measurement errors and the latent coefficients follow normal distributions, we're assuming that they follow a t-distribution. Because with the t-distribution, the degree of freedom can control the robustness. So it's easy to model heavier tail data and also data with potential outliers. They were proved to work well for such data. And it's very easy to implement in Bayesian, because when we specify the model, instead of having set that as a DM, we actually do a DT, that's it. So we only make a very limited change to the model script and we can just use such a robust method. Okay. There are other robust methods available. For example, there are non-parametric Bayesian method, or sometimes called a semi-parametric Bayesian method. This is actually can be treated as an infinite mixture model. So we're going to talk about gross mixture models in part 2 of this workshop. The non-parametric or semi-parametric can be viewed as extension of that. So we're not going to talk about this today, but I just want to make you be aware of this. And also I've developed a robust growth curve modeling based on conditional medians. This is actually a typo here. So it should be a conditional medians instead of the conditional means. When you get your slides from the Moodle website, that will be the correct one. I'll definitely change this after I record this. Okay, so because the traditional growth curve models are really based on the conditional means. So we like I said previously, we average all the trajectory for different individuals. So we model the average or the mean of the intercept, the mean of the slope. But we know that means are not robust to outliers. So instead of using the means, we can use the conditional medians. And that's also can be easily implemented in the Bayesian framework. And also there are other approaches in robust growth curve modeling, and in the practice session, hopefully we'll have time to at least implement robust growth curve modeling using student t-distributions. Okay, so that's about non-normal outcomes, but if the outcomes have binary features or proportion features, or maybe they're count data, then Bayesian methods are also very flexible. If our outcomes are binary, we just simply combine a logistic regression with traditional growth curve models. Okay, so traditionally we'll have this YIT equals B0I plus B1I times T plus the error. But now we just put that model combined with a logistic regression. So instead of having YIT follow a normal distribution, it follow a Bernoulli distribution with the proportion pi IT, and this logit pi IT can be regressed on time. So it's B0I plus B1I times time equals logit pi IT. And then in the second level of the model, we still have the latent interceptions, latent slope, and then they can be modeled maybe just as their mean, or if you have covariates, you can add covariates to this model. So this model can be also generalized to analyze ordinal outcomes by using ordinal logistic regression instead. So it's just very flexible to model binary outcomes. Okay. And if we have proportion outcomes, remember the proportion data or percentage data, they can be modeled using a beta distribution. So here we just consider a beta distribution. Basically, we allow this YIT follow a beta distribution with skill parameter mu IT times phi and shape parameter 1 minus mu IT times phi. So these are the hyperparameters. And by specifying them like this, we can actually guarantee that the expectation of YIT equals mu IT, because the expectation of a beta distribution equals the first hyperparameter divided by the summation of both hyperparameters, and that gives us mu IT. And also we can make sure the variance of YIT equals mu IT times 1 minus mu IT divided by phi plus 1. And here phi can be interpreted as a precision parameter, because if it's getting larger, then the variance will be small. So it's more precise, right? Okay, so for a fixed mu IT, a larger variance of phi just implies a smaller variance of YIT. We can use a beta distribution because it's relatively simpler to implement, but in practice, based on the literature, actually beta distribution is usually doesn't fit the data very well. So instead, we can use beta rectangular. Sometimes there's a simplex method can be used to model proportion data, and those can also be implemented in Bayesian. Okay, okay. And once we specify that, and we can, because this mu IT is actually in between 0 and 1 because it's a proportions. So we can just use a logit link function to link this mu IT with time t. And then a typical growth curve model with proportion outcomes can be expressed like this. So we have this YIT follow this beta distribution with hyperparameters here. And then the hyperparameter of mu IT with a logit link function equals the random intercept plus random slopes times time. And then the second level of the model is the same. And then we also have this precision parameter phi follow a gamma distribution. Okay. Notice that when this YIT, your outcome variable does include a 0 or 1, because proportion data sometimes also includes 0 and 1. And then a 0, 1 inflated beta distribution should be used. So it's just a little bit more complicated than this. I have code to implement this proportion outcomes growth curves. Actually, it's just the code available for a model I just showed you with the BMI and body fat percentage, how they how BMI, the growth of BMI influence the growth of body fat percentage. And there are also time varying and time invariant covariates. So if you're interested, you can definitely run that, and the data and code are all available, and it can be readily run in R. Okay, so in part 3, which is a practice part, we'll have more time to really implement what I just talked about, like the growth curve models. How does that deal with missing data, and also how does that deal with non-normal data? All right, that's part 1, and we'll see you at part 2 now.